Welcome to this session on Gaussian elimination. In this session, we shall implement using a C++ program the Gaussian elimination technique that we had discussed in the last session. We will remember that we had seen a system of linear algebraic equations in n variables can be represented by three matrices. The coefficient matrix would be an n by n matrix. There would be an array of n variables whose values are to be determined and an array of corresponding RHS values. The Gaussian elimination technique, we recall, reduces the coefficient matrix to upper triangular form, making corresponding changes to the right hand side array, and we then use back substitution to calculate values of all variables. Here is a quick recap of some of the representation. This is the general system of linear equations in n variables represented by a matrix which will have the coefficients, the vector of unknown variables and the right hand side vector of values b0 to bn minus 1. The Gaussian elimination reduces the coefficient matrix to an upper triangular form with ones on the diagonal, and using the back substitution we shall be able to solve for the values of all the unknown variables. When a coefficient matrix is reduced to an upper triangular form, we generally get the following system: x0 plus a01 x1 plus a02 x2 etc. The last row will be simply xn minus 1 equal to bn minus 1. Please note that the values of matrix A and B will now be different from the original values, because a lot of computations have gone while we transform the original system into this system, but the back substitution can be applied to calculate values of all the variables. Just as a demo, a system of equations in two variables which we had 2x plus 4y equal to 8 and 4x plus 3y equal to 1, we can represent x by x0 and y by x1. Then we have a two dimensional matrix, 2 by 2 matrix representing these coefficients, where the coefficient values will be 2, 4, a10 is 4, a11 is 3, representing the second row or second equation. Right hand side b0 is b1 is 1, and after reducing the matrix to the upper triangular form, the coefficients will turn out to be like this, where the new values are as indicated. We had seen this last time. We now look at the program gauss.cpp, and let us see how we construct such a program. First, of course, the standard inclusion of IO stream and the declarations of variables. I, j, k will be used as index variables, as is the common practice. N represents the number of unknown variables or represents the system of equations as being of n linear equations. Matrix A represent the coefficient matrix, we have declared it to be 100 by 100. Matrix B correspondingly, the right hand side will have 100 elements, and of course x100, which will not contain anything but eventually will contain the values which we would have calculated for the unknown variables, which can be up to 100. Of course, we assume that the value of n is less than 100. We use additional variables, divisor, factor, sum, the meaning of which will become clear as we proceed. First, we read the input, we get the value of n, we read the matrix A. For simplicity, I have avoided including statements which will validate the input, but the program which will upload on the site will have all those things. Then I will read the matrix B. This completes the input statement. Note again that our standard do loop, for loop that we use will have I equal to 0, I less than n, I plus plus kind of standard structure, because this varies from 0 to n minus 1, and that is exactly the index value for which we need to read the values of the matrix B, or here Aij, which will have two nested loops, one varying I from 0 to n minus 1, the other varying j from 0 to n minus 1. So for every value of I, j will be varied from 0 to n minus 1. Notice that the input will have to be given in the row order, that is 0th row, all values will be input first, then I will become 1, then the row number 1, all values of other columns will be given, etc. etc. We now come to the Gauss elimination proper. Please note that our objective is to get 1 on the diagonal. we start with the first row I equal to 0. Now here the mat AII element need not be 1 originally, but whatever is that element, if we divide the entire row by that element, obviously on the diagonal we will get 1. So we just look at this value, capture it as a divisor variable value and assign 1.0 directly to this. There is no need to divide obviously, because the divisor is same as the value. But now we divide all values in the row by that divisor. Observe that we are doing a transformation to recalculate all coefficients in that row for j equal to I plus 1 to n minus 1, because it is the ith row that we are talking about. So we recalculate I comma jth element of mat A by dividing that element by divisor. We also divide the corresponding right hand side element. So mat Bi is also divided by divisor. Notice what we have done. We have actually transformed the original system by replacing the 0th row by a new row, but which is derived by multiplying that 0th row, original 0th row, by a factor. In this case it is the divisor by which we are dividing. Now if we redo the same thing again and again for I equal to 1, I equal to 2 and I equal to n minus 1, we would have got all of these corrected. Let us look at the subsequent sequence. We have subsequent rows, and in the subsequent rows below this diagonal we need to get all zeros. We now apply the second transformation, namely we subtract the appropriate portion of the ith equation from the next row. So for if I plus 1 is less than n, then for k equal to I plus 1 to k less than n, that is k to n minus 1, we now calculate a factor which is nothing but mat A ki. This is the factor by which we have to take a portion of this row, subtract the ith equation from it. But having taken that portion, we set that to 0, because this will be the column under the I comma ith row, I comma ith element, which is going to be 1. So for j equal to I plus 1 up to n minus 1, we recalculate k comma jth element by subtracting from it a factor times mat ai comma j. Observe, ai comma j is the original row we are looking at, and a factor of that is subtracted from the kth row, and we do this for all values of k from I plus 1 to n minus 1. We do not forget to appropriately modify the kth element of matrix B as well. This simple nested iteration will complete the process of handling one particular portion of the transformation. Now we back substitute starting with the last variable. So we know that xn minus 1 is simply the Bn minus 1th element, and once having got that, for n minus 2 to 0, please note that we are going backwards. N minus 1th value we already got. Now we got to get n minus 2, n minus 3, etc. up to the 0th value. So this is, for once we are using a for loop which moves from a higher value to a lower value, going backwards all the way up to 0. What we do, essentially we sum up the ith row using values of x which we have already determined. So we start with sum equal to 0, and for I plus 1 up to n minus 1, we calculate mat aij into xj into the cumulative sum. Notice that all these xj's have already been determined previously, because j starts only with I plus 1 onwards. Having done this, I simply calculate ith element of x as mat bi minus sum, and when I do that for all values of I would have actually solved the system. This is a very simple, elegant and neat looking solution. Some of you might have difficulty in understanding this in the first instance, but please read this program and also try to execute this program. We need to output the results. So these are standard output statements. First you output the matrix, which is the upper triangular matrix, and then you output the values of x. Here are sample input and output results for your benefit. We have run this program with n equal to 4, the matrix A having these values, and matrix B having these values. You can simply input these values one after another, starting with 4, then this row, and so on. When you do that, when the program is executed, you will actually get these results. First, the matrix A will be printed, which is reduced to upper triangular form. It will be printed something like this, and then values of the variables of x will be printed as 1, 2, 3, 4. In summary then, in this session we wrote a C++ program to implement the Gaussian elimination method for solving simultaneous equations. We saw sample input for a system of 4 equations and the results. Please note that this program is also available on the site as gauss.cpp. Feel free to download it, load it into your code blocks or any other environment in which you are executing these programs, and try it out for these input as well as other input values. Please do look at the problems that you might get when the values that are input represent a peculiar variant of a system of simultaneous equations. Those are the issues which are left to experts in the simultaneous equations, but as far as programming is concerned, you are now equipped to write programs similar to this. Thank you.